Quantum computing is no longer a distant scientific curiosity, it has become one of the most intense technological competitions of the 21st century. Much like the nuclear race of the mid-20th century or the space race between the United States and the Soviet Union, the pursuit of quantum supremacy has drawn in governments, corporations, and academic institutions. This race is not simply about faster computers, it is about fundamentally redefining how computation itself works. To understand why this race is so rare and consequential, one must first grasp what makes quantum computing fundamentally different. Classical computers, the machines that run our phones, laptops, and global infrastructure, operate using bits that can exist in one of two states, 0 or 1. Quantum computers, however, leverage the principles of quantum mechanics, particularly superposition and entanglement. Superposition allows qubits to exist in multiple states. The origins of quantum computing can be traced back to theoretical insights in the late 20th century. In the 1980s, physicists began to realize that classical computers were poorly suited to simulate quantum systems. This led thinkers like Richard Feynman to propose that a computer built on quantum principles could simulate nature far more efficiently. Soon after, David Deutsch formalized the concept of a universal quantum computer. The turning point came in the 1990s with the discovery of quantum algorithms that could outperform classical ones. Most notably, Peter Shor developed an algorithm capable of factoring large numbers exponentially faster than the best-known classical methods. This was not merely an academic breakthrough, it posed a direct threat to modern cryptography. Much of the world's digital security relies on the difficulty of factoring large numbers, particularly in systems like RSA encryption. This realization transformed quantum computing from a theoretical curiosity into a strategic priority. Governments began investing heavily, recognizing that whoever achieved practical quantum computing first would hold immense economic and geopolitical advantages. The United States, China, and the European Union all launched large-scale initiatives to fund research and development. In particular, China has made rapid strides, building national laboratories. At the same time, major technology companies entered the race. IBM, Google, Microsoft, and Intel have all committed significant resources to quantum research. Each company has taken a slightly different approach to building qubits. Some use superconducting circuits, others explore trapped ions or topological qubits. This diversity of approaches reflects the uncertainty and complexity of the field. No one yet knows which method will prove most scalable and reliable. In 2019, the race reached a symbolic milestone when Google announced that it had achieved quantum supremacy. Their quantum processor, named Sycamore, performed a specific task faster than the world's most powerful classical supercomputers. While the practical usefulness of this task was limited, the demonstration was significant. It showed that quantum computers could outperform classical ones in certain domains. Despite these advances, building a practical quantum computer remains extraordinarily difficult. Qubits are highly sensitive to their environment, and even the slightest interference can cause errors, a phenomenon known as decoherence. Maintaining quantum states requires extremely low temperatures, often just fractions of a degree above absolute zero. Error correction, a relatively straightforward process in classical computing, becomes vastly more complex in quantum systems. Yet the potential rewards are immense. Quantum computers could revolutionize fields ranging from medicine to materials science. They could simulate complex molecules, leading to the discovery of new drugs and more efficient chemical processes. In finance, they could optimize portfolios and model risk with unprecedented accuracy. In logistics, they could solve complex optimization problems that are currently intractable.